Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we simply continue our previous discussion on motion of a particle under different type of constraints. So, already I have introduced several type of constraints. If you remember that before even classifying the constraints, I defined constraints in the framework of classical mechanics. Constraints are nothing but the conditions or some limitations imposed on the kinematics of the particle. Okay. So, I am just trying to emphasize on this point that if, for example, if the force nature is specifically following some symmetric property, for example, like the central force, that force is a function of the modulus of r, okay, and force is directed along the line joining the particle and some source or the origin of the force. Okay. So, this is a constraint on the force, if you want to say. Okay. So, this is a limitation or it is a specific type of force. So, can we call this is a constraint? No. In this context, we will not call that as a constraint. Okay. So, we will simply try to do the constraints, I mean try to limit ourselves to conditions and limitations which are imposed on the trajectory, on the velocity of the particle. Okay. So, you can also have something a little bit complicated than that. So, for example, you can say that some combination of velocity is related to some combination of the position coordinates. Okay. That is also possible. So, for example, in the last lecture I gave an example of this if you have a constraint like where x dot is equal to lambda times x y. Okay, lambda is a constant, then your x component of velocity is actually proportional to the product of the position coordinates x and y. Okay. So, in this case you see that this is not I mean just merely a constraint only on the trajectory or only on the velocity, but it is a mixture of two. Also we can say that the constraints can consist of time explicitly, and so for example, just for a simple pendulum whose length is changing with time or an inclined plane whose angle is changing with time, they can be thought to be the examples of constraints with explicit time dependence, and those constraints we called that rheonomic constraints, whereas the constraints without explicit time dependence we called scleronomic constraints. So, once again, so rheonomic and scleronomic, that is depending on their time dependence. Of course, dependence means explicit dependence. Okay. Then we talked about unilateral and bilateral constraints. We said that if a constraint is a form of equation, then this is a bilateral constraint. If it is consisting of inequalities or a combination of inequality and equality, then it is called a unilateral constraint. Then the most important one, the holonomic constraint and non-holonomic constraint. Okay. So, holonomic we said that it has several features. First, it should be an integrable form of equation, which we sometimes loosely say algebraic, but it actually can also consist of trigonometric or exponential type of functions as well, which we know how to integrate. Okay. So, I can actually write algebraic or trigonometric or exponential or a mixture of them. Okay. Some functions like that. Okay. Then it should be always, so it is an equation, it should be integrable, then it can consist only position coordinates and at best time explicitly. Okay. Finally, we say that holonomic constraint is such a constraint which is actually able to reduce the number of useful coordinates in the problem. So, just remember the case for a simple pendulum where if we say that the length L of the pendulum is fixed in time, then this is x direction, this is z direction, okay. Then x square plus z square is equal to L square makes actually the situation simpler, because then you can actually write every x to be equal to root over L square minus z square, okay. And of course, you can take plus minus according to your convention. Okay. For example, here in this problem z is directing vertically upward. So, we know all these coordinates vertically downward, I mean from this point which can be considered as origin. Okay. From this point every displacement is having a coordinate z coordinate which is negative. So, z should be negative. So, when we calculate z, that will be actually minus root over L square minus x square. Okay. These things we should just keep in mind, okay, while solving a problem. Then we also said that it is not always compulsory that the a priori form of a holonomic constraint is containing only position coordinate and time. Sometimes it can be possible that the a priori form, that the apparent form of the holonomic constraint is actually containing velocities, but in such a way that they can be integrated to reduce the equation in a form where you can actually have x, y, z and t. So, the position coordinates and the time. So, for example, I said that if you simply say x dot equal to lambda z dot for a 2D problem like this, okay, then actually this is nothing but equal to x is equal to lambda z plus c. This c you can get rid of, okay, by just choosing suitable initial conditions. Okay. So, you can simply say that okay, I choose my origin in such a way that when z is equal to 0, my x is equal to 0, then actually c is 0 and your x is equal to simply lambda z. Okay. So, you are in any case you see this is nothing but a holonomic constraint. Okay. And this type of forms which are actually holonomic, but does not look like a holonomic at first sight, okay, they are known as pseudo holonomic constraints. Okay. Then we said that in nature, whenever a particle is undergoing a holonomic constraint, most of the cases they are associated with some force of constraints. And for example, in the case of a simple pendulum, so I can draw here. In the case of the simple pendulum, okay, so this is at any arbitrary position. Okay. If I say that the string is of fixed length, then it always has some t to maintain the length. Also, if I say that length is not constant, but is a function of time, okay, so let us say L0 1 plus sin omega t, okay, even then it should have a tension, okay, but that tension can actually vary now. Okay. But then we actually also showed that one good thing is that, so if the length is just independent of time, is constant in time, then in this case the tension force is actually perpendicular to the direction of the motion of the particle, okay, that we all know. Okay. Now, if we are considering another case where a particle is actually sliding, okay, a particle is actually moving, I should not use the word slide because it somehow assumes a surface. Okay. So, just the particle is moving downwards along this inclined plane with this angle theta, and we are simply saying that it is always necessary for the particle, we impose the condition that the particle should be always at the contact of this surface. Then we know that there should be, due to this contact, there should be a normal reaction force R, okay, and which is also if you see that which is also perpendicular to the direction of the motion of the particle. However, in this case also I said that if your theta changes with time, for example, let us say at a time instant t1 the theta is theta 1, but at time instant t2 the theta is actually, let us say, I would actually do something like this, a different surface like this, theta 2, and then what this particle would have, actually the particle will at this point, okay. So, you see now in order to maintain the constraint that the particle will always be on the surface of this inclined plane, the particle should go in the direction which is like this, but again the reaction force is directed perpendicular to the inclined plane where the particle is instantaneously located. And that is why you will see that whenever this theta is also changing as a function of time, then this reaction force is no longer perpendicular to this case, and this is also very similar to the case of this pendulum where the length of the string is actually changing explicitly with time. Okay. In both cases we said that we have one smart trick to get rid of this thing. First of all, if these reaction forces and these tension forces can be somehow classified under a universal umbrella, we can actually think that they are actually coming because we are posing some constraint, and due to that constraint there is a somehow a contact or some commitment of that medium. For example, whenever this mass is attached to the string, okay, the string is actually trying to respond to that attachment of mass. Also, when the particle is moving on this surface, the particle touches the surface and then the surface also wants to respond to the particle. Okay. And that is why they are called somehow some forces of constraints, and which are actually coming from a very intrinsic property like elasticity, rigidity, all this type of properties of the material, okay, on which or to which the particle is attached. Okay. So, these forces of constraints in general for our usual everyday problem associating one particle motion, we see that they are actually perpendicular to the infinitesimal displacement of the particle. Okay. Just for example, here the reaction force, here the tension force. But if this constraint force is an explicit function of time, then this is not necessarily perpendicular. So, if you just consider a real displacement, then the work done by the forces of constraint is 0 when you are talking about time independent constraints. But if your constraints are explicit functions of time, then basically you have to consider a new thing which I introduced, that is the virtual displacement. We can actually show, if we instead of considering real displacement, if we constitute a virtual displacement, this is a displacement which you cannot see during the motion of the particle, but what you can actually imagine and you actually can visualize virtually in your brain, that is in your brain due to between the two possible configurations, okay, both are compatible with your constraints, but at a given time instant. What is the meaning? The meaning is that you can just prepare your system, okay, and you say, okay, my simple pendulum system, let us say I have prepared this in my lab, and at some t is equal to 0, I am just letting this particle to move from this point. In another experimental setup, you just make an initial displacement which is here. Okay. In both these experiments, you see that there will be actually there will be a discrepancy in this, okay, but this is not possible in one single experiment, or you can say I am just setting up one experiment and this is just a thought experiment, I am thinking that in my brain for the second one, okay, and then you say at t is equal to 0, in my real system the particle's initial position is like say x0 1, and in my brain I have another configuration where the particle starts from x02. So, x01 minus x02 is the virtual displacement, okay, for the coordinate x. Okay. Now, for virtual displacement concept, we always use the concept of infinitesimal displacement. Okay. Otherwise, there are some other problems. Okay. So, just for this course, this is very important to understand that virtual displacements are useful in infinitesimal sense. Okay. So, that means we always write delta r. Okay. So, dr means that your time is evolving, and that is why your particle is starting from this point, it may come to this point. Okay. Virtual displacement says that no, you are just making two setups, maybe two in reality, or you are making one setup in reality and another one you are thinking in your brain, and then you fix your time point. So, although this is a function of time, now since you are fixing a time point, let us say t is equal to 0 or t is equal to 2, your L is now fixed, and that is why your imaginary system, okay, will also have a position which actually remains on the arc of the same circle as that of your real system, okay, for example, for a given instant of time, given instant. Okay. So, that is very important. If they are all satisfied, then we say that F c, so the constraint force dot delta r is equal to 0. Okay. That is the principle of virtual work we said, and from that also we said that okay, if for a particle of mass m, if r double dot is the acceleration, then the total force acting on this is the force due to some external field, okay, or some external effect, and the force, so which I called Fi, and some force of constraint Fc. Then if I do a contraction with delta r in both sides, you will actually have this term to be equal to 0, and that is why you will have m r double dot minus Fi, okay, dot delta r is equal to 0. Okay. Here I did not say that this is 0, this is simply perpendicular to this, okay, both for rheonomic and scleronomic holonomic constraints. Okay. And that is why this is an equation of dynamics as well, okay, where you can solve the system, solve the motion of the particle even without introducing the constant forces, okay, because you see the constant forces are going away. So, this is known as the D'Alembert's principle. So, today we will start from there, and after this I presented a simple example of a simple pendulum, okay, where the length of the string is fixed, and I told you to try to use this principle of D'Alembert, okay, for solving the motion of a simple pendulum whose length of the string is changing with time. Okay. Then today I will present another way, a subtly different way from this one, this principle, but where we will also use the constraints explicitly with their mathematical forms. So, in today's lecture we will discuss actually the method of Lagrange equation of first kind. So, you can easily see that I can actually say that from D'Alembert's principle, I can say that m r double dot minus f I dot delta r is equal to 0, that we know, okay. And we actually used that thing, okay, along with the constraint itself. So, we said that, okay, if there is a constraint, let us say, okay, so from this you will have some conditions and then you separately use the constraint and then you like actually eliminate those delta x, delta y, delta z, and finally you find the solution of motion, okay. Finally you find the equation of dynamics, okay. Now, from D'Alembert's principle we can get this. Here we will do something much more interesting. We actually involve the constraints together with this equation. So, now we consider a constraint which is holonomic. Okay. So, holonomic means that they should have a function phi which can involve maximum all these 3 coordinates and t is equal to 0. Let us say I am just talking of a very simple system, one single particle moving in 3D space and I have one constraint, one holonomic constraint, okay. So, which is given by this, okay. That can be actually, if you see, so this function, okay. So, for a simple pendulum moving in xz plane, this phi is given by x square plus z square minus L square, okay. For a particle moving on the surface of a sphere of radius capital R is given by x square plus y square plus z square minus r square, okay. Of course, here if L is a function of t, then instead of just writing L as constant, you can actually write also L0 square 1 plus, for example, sin omega t whole square, okay. Here you can also write some r, if r is equal to some alpha t, then you can write alpha t whole square like this, okay. So, this is somehow the general form of a holonomic constraint. If this is a holonomic constraint, what is the differential form of this holonomic constraint? D phi. So, this is actually a scalar function here, okay, and so d phi will simply be equal to del phi del x dx plus del phi del y dy plus del phi del z dz plus del phi del t dt, okay. So, this is when we are just talking of change in phi, okay, in a real evolution where you have real displacements and real interval of time. But if we now do for virtual displacements delta r, okay, where time is frozen, okay, we have d phi will be equal to, so then I will actually do not use d phi, I will use this thing as delta phi, okay, and that will be equal to del phi del x delta x plus del phi del y delta y plus del phi del z delta z. You see all these 3 things, they are actually virtual, okay. What about this term? There will be no term here, okay, which is a counterpart of this term, okay. So, because delta t is 0, as delta t by definition is 0, okay. So, I will have simply this. If you have this thing, then you actually have this is equal to, because phi is 0, okay, this is the definition, this will also be equal to 0, okay. Now, you can also write this thing in Cartesian coordinate system, okay. So, here we have used Cartesian coordinate system, okay. You can also write here m x double dot minus f x, okay, delta x plus m y double dot minus f y delta y plus m z double dot minus f z delta z, that is equal to 0. So, I have now two equations. One is this, where delta x, delta y, delta z are related by some other functions and finally gives a result which is 0. Okay. And I have this, where also some combinations of delta x, delta y and delta z, they are adding up to be 0. Okay. So, of course, you know that if I add two zeros, I will also have 0, but I can do something more general. I can actually write, I can take one of this equation intact and actually I can multiply an arbitrary scalar quantity, let us say number, let us say lambda. Okay. If I just multiply with this, this will remain 0, and if I actually add this now to this one, it will still remain 0. So, mathematically if you say that okay, you have two equations, one is like this and another is like this, okay, then since both of them are 0, instead of just saying that this plus this is 0, another more general possibility is that you write some constant time this one plus some constant time this one is also 0. Instead of saying that individually they are 0 and their exact sum is 0, another more general mathematical conclusion is that if you multiply some arbitrary function here, so let us say some m1 here and some m2 here, okay, and then you add, then also you will get 0. So, instead of m1 and m2, I just say that call this lambda as m2 by m1, okay, and I just get rid of two functions. I just say that okay, I just keep this equation intact and multiply this equation by a function lambda, okay, but it should be multiplied uniformly by this function lambda, and then if you add, you will still have 0. So, finally, adding the above equations, we get m x double dot minus f x plus lambda del phi del x delta x plus m y double dot minus f y plus lambda del phi del y delta y, okay, and finally you can say plus m z double dot minus f z plus lambda del phi del z delta z is equal to 0. Once again you see in this equation there is no force of constraint, okay. But now we have written these two explicitly, that is the D'Alembert's principle and the part of the constraint explicitly together, okay. So, if we write these things, then we actually can say okay, what is the vector form of this? So, vector form is simply m r double dot minus f, okay, or as you wrote f I, for example, the part of force which is not related to the constraints, okay, and then you will have plus lambda. So, del phi del x you can take like just component wise, you can now think that this is coming from. So, these things actually come from this vector lambda del phi del x I cap plus del phi del y j cap plus del phi del z k cap, and which is nothing but equal to lambda gradient of phi, okay. So, I can write lambda gradient of phi is equal to 0. This is known as the Lagrange's equation of first kind. So, this is actually not primarily very different from D'Alembert's principle. D'Alembert's principle said that okay, I have this part, this first two terms dot delta r is equal to 0, and then I again take separately the constraints, and I actually from that constraints I actually try to find a form where something dot delta r is also 0, and then I do the same thing here. Okay. On the other hand, here what I am doing right from the beginning, I take the constraint, okay, taking this as for simplicity as a holonomic constraint, and for which you have this actually specific form, this form, and you finally can show that this is given by this one. Okay. So, this is a little bit at this point I have done a cheating in general. It is not a cheating, I am coming to that point. So, I have said okay, if this is 0, is this plus this is equal to 0, this is equal to 0. This is possible only when we assume or we can show that delta x, delta y and delta z, they are arbitrarily chosen, or they can be arbitrarily chosen, that means they are independent. But remember, delta x, delta y, delta z, they are related by constraints. So, they are not independent quantities. Okay. See, if they are not independent quantities, because they should always be related by the constraint equation. So, for example, if you just remember that x square plus z square is equal to L square, simply gives you that 2x delta x plus 2z delta z equal to 0. So, delta x and delta z, if they are independent, then actually x and z should be 0, and that is not possible because everything is then 0 identically always. Okay. So, always this means that the particle is sitting at origin, which has no meaning here. Okay. So, delta x, delta y, delta z, they are not in general independent. So, right from this equation I cannot come to this. What I have to do, I can say, so okay, since they are not independent, in general for any arbitrary value of lambda, I cannot claim this thing and this thing, they are 0. But I can now ask this question, is there any possible value of lambda for which even if delta x, delta y, delta z, they are for which even if delta x, delta y, delta z, they are not independent, finally I can write mr double dot minus fi plus lambda gradient of phi is equal to 0. This is a question. Actually, you can show that yes, there exists a specific value or a specific functional form of lambda. Okay. So, lambda is actually a function of x, y, z. Okay. For the time being, I just write x, y, z. Okay. Yeah. It can be a function of t as well. Okay. So, if the lambda is a function for which although they are not independent, okay, this can be true. This can be true for a specific value, a specific functional form of lambda. Okay. And this lambda is known as undetermined multiplier of Lagrange. If you really want to know a little bit more about undetermined multipliers of Lagrange, which is mathematically a very sound technique, you can go through good material on internet. I do not have any specific suggestion, but just read it, and if you have any question, you can always come back to me through forum. Okay. So, now you just admit that, okay, I admit there exist a specific form of function for lambda for which this is still 0, even if these things are not arbitrarily chosen. Okay. And we will now just with this claim we can say that this equation is a valid equation and this is the Lagrange's equation of first kind. So, with the assumption that there exists a specific functional form for lambda for which this thing in the green box is true, I can talk of Lagrange's equation of first kind. So, before wrapping this lecture up, I want to mention somehow two very interesting points about this Lagrange's equation of first kind. The first thing is that here we have done a very simple case with only one constraint. Now, it can have actually more than one constraints. So, for a motion in 3D space you can actually have more than one constraints. So, let us say two constraints. One can be actually say that x is equal to some a cos omega t and then y square plus z square is equal to some a square, if you have such things. So, first of all you have to make that these constraints are holonomic. Now, for every single holonomic constraints actually one undetermined Lagrange's multiplier comes into play. So, if you have two holonomic constraints, then actually you have to introduce two undetermined multipliers, for example, lambda 1 and lambda 2. So, because then actually what you will have two equations like phi 1 equal to 0 and phi 2 equal to 0, and then actually you will have some equation like delta phi which is equal to 0, then you will have delta phi 1 which is 0 and delta phi 2 which is also 0, and that is why you will have two different multipliers of Lagrange. I will give you an interesting problem on that in the assignment. The final thing is that although for the sake of this course, which is a very introductory level course, I have just introduced the Lagrange's equation of first kind exclusively with the holonomic constraints. It is not necessary that the constraint should be strictly holonomic. If a constraint has a specific form called a Pfaffian form, but this constraint is not holonomic, that means it contains actually an equation involving even velocities in addition to position coordinates and time, then also for certain form of non-holonomic constraints you can also use this method of Lagrange's undetermined multiplier, and you can use Lagrange's equation of first kind to solve a problem. This type of problem is now beyond the scope of our current interest of this course, but if you are interested you can always go through very good books. For example, Goldstein books, you can see some examples discussed on this matter. Thank you very much.